So now we're going to do a bit of a problem that talks about the first law, now that we know a little bit more about how to find U. So as shown in this figure at the bottom, a system consists of a copper tank whose mass is 13 kilograms, 4 kilograms of liquid water, and an electrical resistor of negligible mass. The system is insulated on its outer surface. Initially, the temperature of the copper is 27 degrees Celsius and the temperature of the water is 50 degrees Celsius. The electrical resistor transfers 100 kilojoules of energy to the system. Eventually, the system comes to equilibrium. Determine the final equilibrium temperature in degrees Celsius. So, we'll follow our solution process. We want to write down our known information. We have a mass of copper, 13 kilograms, a mass of water. We have the mass of the resistor, which we're going to assume is very small, approximately 0, compared to the mass of the copper and the mass of the water. We know the initial temperature of the copper is 27 degrees Celsius. The initial temperature of the water is 50 degrees Celsius. We know that some amount of time passes between 1 and 2, and it's enough time that the system comes to equilibrium. So I don't know that we've used that word before, equilibrium. So here it means that the temperatures here will become equal. So we'll get to a point where everything is equal, right? So it's at equilibrium. This typically takes a fairly long time. If you think about you boil some water for macaroni and cheese, but you forgot to put the macaroni in it or something, or maybe you just left it on the pot after you stopped cooking it because you had to go outside and do something. Eventually, over time, the macaroni and the liquid in that pot will get back to room temperature. So then everything is at equilibrium again. The energy from the resistor is 100 kilojoules into the system. We're going to also assume that our system has an insulated surface around it so that no heat or work can come in or out. What are we required to find? We want to know the temperature in degrees Celsius once everything hits equilibrium. So here I have my system, which is perfectly insulated. That's, I guess, what this speckled border is around my system. I have a resistor, which is heating up the copper, and then I have liquid water on the inside. So this is like an electrical heater, right? I know if I draw out my temperature and my time here that I have copper, which is initially at 27 degrees Celsius, water, which is initially at 50 degrees Celsius, and eventually they're going to come to some equilibrium temperature. But I'm adding energy into the system, so I don't know if this temperature is going to be between these two values or potentially above this value too. So I'm going to make two different tables to solve this problem. The first is a state table, which we've been doing a little bit. So I have the water, right? I know its initial temperature, and I have the copper's initial temperature, but I'll also get some information for the water and the copper at the final temperature as well. And then I'll make a process table as I go from state 1 to state 2, how much heat is added and how much work leaves the system. So let's start. We're going to state and justify some assumptions. So here, I'm going to assume, because as we move from state 1 to state 2, that everything is insulated so that there's no heat coming in or out of my system. I know, or at least I'm going to assume, that the temperature of the copper and the water at state 2 is going to be equal. So there's really only one T2. So if I'm looking at the state of my different materials here, so I have two different materials, one is copper and one is liquid. So here I'm using X, which we've typically been reserving for quality, and I would probably encourage you to do that. But here I'm just trying to say what the phase of my different materials are. So the copper, I think, is going to remain solid. I don't think we're putting enough energy into the system for the copper to melt. We're probably also not putting enough energy into the system for the liquid to boil. So I'm going to assume, at least initially, that I'm moving from one subcooled liquid state to another subcooled liquid state. We'll check, because I'm going to assume that my pressure is approximately atmospheric pressure here. So if my temperature gets above 100 degrees, then maybe I'll have to revisit this assumption. That's why it's an assumption, because I don't really know if it's true, but I'm going to guess. at the end of the problem, I'll check. Here, my specific heats, I'm going to say are constant for both the water and the copper, so that the specific internal energy is changing on a constant slope with temperature for both the water and the copper. But those specific heats will be different because they're different materials. And for the delta U, so the change in internal energy, I'll make the assumption that the water is liquid, so that it moves from one subcooled liquid state to another subcooled liquid state. So I can use CV times delta T. For the copper, which is a solid, we can use the same equation. So my solution, my first law, I'm going to assume that the kinetic and potential energies are small, so I'm only interested in delta U. So the left-hand side of my equation here becomes the change in U for copper plus the change in U for water is equal to Q, so the heat that comes in minus the work that goes out. Now, the important thing here is that when we're talking about these changes in internal energy, we always end with we start with the end state and we end with the beginning state. So this is U at the end minus U at the beginning. So it's always going to be U2 minus U1. Now, we've said that the system is insulated so that there's no heat coming into our system. So now when I apply my approximations that I can use CV times delta T to find delta U for both of these systems. But if I say CV times delta T, that gives me the change in the specific internal energy. So I want to multiply by the mass, and I didn't keep the subscript here, but in this term where we're talking about the copper, this is the mass of the copper. And in the term where we're talking about the water, this is the mass of the water. So this is nice. I know most of the things on the left-hand side. I know the mass of the copper. I don't know T2, but I do know T1. I know the mass of the water. I don't know T2, but it'll be the same as T2 for the copper. And I do know T1 for the water. So the things that I don't know here are the specific heats, T2, and the work. And this is not too bad. I can look up the specific heats in the textbook. So the specific heat for copper is 0.386 kilojoules per kilogram Kelvin. Now, the specific heat for water is 4.18 kilojoules per kilogram Kelvin. Now, you see that there's a pretty big difference, more than a factor of 10 between these two numbers. Copper is a great conductor of heat, so it doesn't take too much energy to increase the temperature of copper. The temperature of water, as we know, right, we keep saying a watch pot never boils. It takes a lot of energy to increase the temperature of water by even just a degree. The trickier part is the work. So this energy that's coming in electrically could be used to move something. So to apply a force over a distance. So we can think about this as work if we want. Now, this is energy that's coming into our system. So if we think about this as work, then this would be work in to our system, and work in is negative. I could have set this problem up so that I thought about there being no work here, and I thought about this energy coming in as heat. And if I did that, heat in would be positive. So if I thought of this as a Q, then the sign would change because of the sign conventions, right? Heat in is positive and work in is negative. So it's going to end up being the same on the right-hand side of my equation, 100 kilojoules, no matter which one that I choose. So don't get too worked up if you would have thought that this would have been a heat and not a work. I don't know what T2 is, but I do know that it's the same for copper and for water. So here, if I work this out, I could isolate T2. That's the only thing I don't know now. So I know the mass of copper. I know the specific heat of copper. I know T1 of copper. I know all that same stuff for water, and I know the work. So the only thing that I don't know here is T2. So I can go through and I can isolate this equation for T2. And I can see that T2 is 49.3 degrees. That's it for today. I look forward to seeing you next time on Thermodynamics.